Hi, we're Team Gangrene, and this is our ACI Ecoconcrete project. To get started, we're going to talk about our concrete mix design. So for our base case scenario, we used 100% type 1 Portland cement. All of our values were determined using the PCA manual and the requirements set by the rules for the project. Our water to cement ratio was 0.4. Our designated slump was 3 to 4 inches, and we chose a nominal maximum aggregate size of 1 inch. On the right, there's a table showing all of our quantities for cementitious materials, aggregates, and water, and we did not use any admixtures in our base case.
So our alternative case scenario was created using the ACI LCA calculation tool and while also keeping the competition constraints in mind. For our cementitious materials, we decided to use 60% type 1 Portland cement, 38% fly ash, and 2% silica fume. We had a water to cement ratio of 0.4 and a slump of 3 to 4 inches. And we chose a nominal maximum aggregate size of 1 inch. And the table on the right shows the details of our mixture, such as our aggregates and water, and we used no admixtures.
Here we have our materials selected for the design mix. The table shows aggregates, water, and the 3 admixtures. The admixtures considered for the alternative case mix were fly ash, silica fume, and blast furnace slag. You can also see on this chart the companies which the materials to be ordered from, which was determined based on shipping distances to Driftmeyer in order to reduce transportation emissions. The distances are also displayed that each truck is to travel. These admixtures used were selected in order to increase the service life as well as decrease the environmental impact.
Now we'll move on to explaining the methodology we used when creating our alternate case mixes. After the creation of our BCS mix, we used Excel in conjunction with the LCA Ecoconcrete tool, as well as Life 365. And by varying the percent replacement of cementitious materials, fly ash, slag, and silica, we came up with this chart that has all the possibilities. After the optimization using the Excel solver tool, we came up with this final optimum ACS optimized mix.
Our decision-making process relied heavily on the environmental impact of each of the supplementary cementitious materials. Silica fume has a greater environmental impact than Portland cement on carcinogens, ozone depletion, and ecotoxicity, and is comparable in terms of fossil fuel depletion. Fly ash is the most commonly used mineral admixture and similar to silica fume. It also can increase the compressive strength of the concrete. Fly ash has a positive environmental impact on all 5 analyzed parameters, creating less emissions than Portland cement in all 5 of those. And then granulated blast furnace slag has a positive environmental impact on global warming, ozone depletion, and fossil fuel depletion, but has little to no impact on carcinogens and ecotoxicity. So based on the 5 parameters for each of these 3 supplementary cementitious materials, we optimized for the best mix. We used the total of 40% of supplementary cementitious materials to maximize the environmental impact, and then also use the correct mixture to increase the life expectancy. So a small percentage of silica fume was good because it increased the lifespan and had considerable environmental impact. And then we did not end up using the blast furnace slag simply because the environmental impact was not strong enough to rationally use in it.
As Jack said, the environmental impact played a huge role in designing our alternative case design. So with the use of the ACI LLC tool to establish a base environmental impact that our original design had from the following categories below, we then used the mixture designs from our Life 365 model, which we were able to see which admixtures improve the environmental impact from the base design. And then for our LCA, we used a cradle to grade approach, when looking at each admixture material, meaning everything from the extraction of the material to the transport to the lab was involved in this LCA. So that means that we had to find the closest source for each admixture to the Driftmeyer lab, which we had used to cut down the environmental impact. Like Jack said, fly ash has a better impact on the life expectancy of the concrete and was clearly better at improving the environmental impact. So we decided to use 60% cement, 38% fly ash, and 2% silica fume, which resulted in an increase of service life by 17.6 years and 18.3% decrease in the environmental impact of the concrete. Thanks everyone for watching, and that is our ACI Greencrete.